The purpose of Lab 4 was to observe the oscillating motion of a spring with a mass attached to the end. By using Newton's second law to observe the motion of the mass to determine the causes of the motion, and then applying the energy principle, which states that the total energy exchange of the system with the surroundings equals the sum of the kinetic energy and potential energies, we can construct a VPython model which recreates both the predicted and observed motion of the spring. To begin, it is important that we understand the fundamental principles behind this lab. Let's start with Newton's second law. As stated in previous labs, Newton's second law takes measurable quantities such as mass, velocity, and change in time, and is able to produce a net force that causes the object's motion. In this lab, the mass of the spring system was 0.402 kilograms, with the zero vector as the initial velocity, and a position in the third quadrant of the coordinate axes set in tracker. Applying this to our VPython code, you can see that the mass of the ball, the initial positions and velocity, as well as the starting time are accounted for. These two lines of code can be found within the while loop of the code, as they are constantly updating the velocity and position of the spring with increasing time. But it may still be unclear how we find the net force. To find F net, we need to add up all the forces acting upon our spring mass system. The first force acting on our system is the spring force. This force is calculated by multiplying the spring constant K sub s by the amount the spring was stretched from its length at rest in the direction L hat that restores the spring to its original state. These calculations were done using the data extracted from my video in Tracker. Applying this to our VPython code, you can see Earth's gravitational constant g, the calculated spring constant, and L naught. This part of the code also calculates the changing length of the spring throughout its motion. S, or L minus L naught, changes constantly, so we cannot simply plug in a single value. In the while loop, we calculate the spring force given this expression. The second force acting on our system is the gravitational force. This force is calculated by multiplying the mass of the system by Earth's gravitational constant g and the negative y direction. This is also accounted for in the while loop of the VPython code. Now that we have calculated all of the forces, we can update the code to set net force equal to the spring force plus the gravitational force. Also included in our code is the energy principle. The energy principle states that the total change in energy is equal to the change in kinetic energy plus the change in potential energy. Based on the system we choose in this lab, the total change in energy is equal to 0. The potential energy of the system has to include the potential energy of the spring and the potential energy of gravity. All of these values can be calculated given these equations. These equations are rewritten as code in VPython with each of the initial energies defined as well. Energy changes must be calculated within the while loop because the energy of the system changes as the position and velocity of the spring mass system itself changes. These changes in energy are plotted in the VPython program, and the results can be seen in this chart. The blue lines represent the oscillating kinetic energy with time. The red lines represent the oscillating potential energy of the spring with time. The green line represents the oscillating gravitational potential energy with time, and the yellow line represents the sum of all of these energies, or the total change in energy. Here is the video we were asked to analyze in Tracker. As you can see, the origin was placed at the point where the spring is attached to its base, which is 0.7 meters above where the spring hangs at rest. The length was calibrated using the resting length of the spring. And when we play the video, you can see that the graph to the right shows the oscillating or sinusoidal motion of the spring, while the chart in the bottom right corner contains the data that was converted into a CSV file and imported into the VPython program to recreate the observed motion. Given all of our code and the data and calculations from Tracker, we can run the code to provide a visual representation of the predicted motion that VPython calculates versus the observed motion that VPython reads out of a CSV file containing the data. When we run the code, we see that the two motions, observed and predicted, red being the observed motion and blue being the predicted motion, are very similar to one another, which is good. It shows that the fundamental physics we explained earlier can be used to predict the motion of an oscillating object. The discrepancies in the motion, which can graphically be seen here, are most likely due to error in tracking the video. What does it mean? The first question asks, is energy principle satisfied? And looking at this graphical representation of the motion, we can see that although the delta K, which is the kinetic energy, and both of the potential energies, the spring potential energy and the gravitational potential energy, all oscillate, the total energy, which is represented by the yellow line, is a straight line at 0, which means that the total energy adds up to 0, which in fact satisfies the energy principle. The second what does it mean question involves a comparison of the oscillating period of a spring given x positions to the period given y positions. After calculating the period, or the time to complete one cycle, the average period given y positions was 1.524 seconds. Repeating this process for the x positions, the period was found to be 1.638 seconds. The reason for the discrepancy between these two numbers could be the result of the Earth's effect on the system in the y direction. The period given y positions more accurately represents the time to complete a full cycle because it is directly affected by both the spring and weight forces, whereas the period given by x positions acts more like a pendulum and is not affected by the forces until the ends of the cycle.